will, as I said in the last lecture, we will now after having stated the central limit theorem, talk to you about its importance. We will actually see now, once I prove the theorem and then I give you applications, you will see how important the theorem is and how widely used and the theorem is. Okay. So, as we said that the central limit theorem says that if you have the sequence of identically independently distributed random variables with mean and variance finite, then we say that the sum of these random variables x 1 plus x 2 plus x n, it will have mean n mu and variance n sigma square. So, this will this will converge to n 0 1 as n goes to infinity. That means, the distribution, no matter what the original distribution of the exercise was, now when you take the sum and you let n go to infinity, then this random variable will converge to the standard normal variate. So, this is convergence in distribution, right, or in other words, as we can state it in another way also, this is for any a which is from minus infinity to infinity, a finite number, then the probability of this number being less than or equal to this random variable less than or equal to a will converge to the standard normal. That means, this is your f z a, right, and this is your f z n a. So, this converges to this as n goes to infinity. So, in distribution the convergence is there, right. Now, in order to prove this, I need to use this lemma which talks about uniqueness of the MGF, and I will not give a proof for this, we will just accept the lemma as it is. So, this says that if z 1, z 2, z n again is a sequence of random variables having distribution functions f z n and MGF m z n, right, and greater than or equal to 1. So, the distribution function is f z n and the MGF of z n would be m z n and greater than or equal to 1. Let z be a random variable having f z as its distribution function and m z at its MGF, right. So, then we if m z n t converges to m z t, that means, as n goes to infinity, this moment generating function converges to the moment generating function of the variate z, then we say that the corresponding distribution functions will also converge to the distribution function of z. That means, so this talks about the uniqueness of the MGF. That means, if the MGFs m z and t converge to m z t for the variate z, the MGF of z is m z t as n goes to infinity, then the corresponding distribution function of z n, which is f z n t, will converge to the distribution function of z for at all points t at which f z t is continuous, which means that it is defined, right. So, this is the idea. That means, the MGFs uniquely, and while discussing MGFs, I also tried to tell you that MGFs uniquely give you your density function or the distribution function, because the parameters you can compute and actually not only the parameters, but the distributions are is the same. I mean, once you get a MGF, you can uniquely fix the distribution, right, from the form of the MGF function. So, this is what we are stating here, which we have also been using otherwise. So, now let us, so the proof is not very difficult, it is straightforward. So, I am just rewriting this function, this random variable. So, mu is getting attaching to each of the xi's. So, therefore, the same thing can. So, now I am writing the MGF of the random variable, which we want to show will converge to a standard normal variate in distribution. So, this can be at a point t, I am defining the MGF. So, this is in fact e raised to this whole thing into t, right. The MGF of this would be e raised to whatever you want to call it, y n or something, or z n, then e raised to z n t. So, the MGF expected value of e raised to z n t, you can say, right, which I can write as x 1 minus mu upon sigma root n plus x 2 minus mu and so on. Now, since x 1, x 2, x n are identically distributed and independent random variables. So, the MGF here, again by the property of the MGF, Well, okay. The thing is that yes, I should have okay. So, yes, the order has been a little, because I will be talking of the MGFs of the independent random variables, more than one variable. So, that should have come, the lecture should have come before that. Okay, anyway, we can talk about it. So, what I am saying here is that this MGF can be written as the product of the MGF of x 1 minus mu upon sigma root n raised to n, because of the independence. This anyway also follows from independence, because you see when you write this, let me say I am saying z 1 plus z n and you are taking t. So, when you write expectation of this, right, because the PDFs are, so this will be z 1 into f z n, because the joint density function would be this, right. So, your expectation when you write of this would be whatever you can, nth order integral from minus infinity to infinity, depending on if the variates are defined. I am taking the general definition into d z 1 d z n, right. So, then you see you can separate out the integrals, and so each integral will be the MGF of these, and since they are identical, it will be the same, right. I am writing f z 1 f z n, but they are all the same, f z 1 f z 1. So, therefore, you can immediately see from here that this will be this MGF can be written as this, because of independence and identically distributed random variables. Now, this I can write as, okay, this should have been at t, MGF at t, right. And so, let me just separate out this. So, this will be MGF of x 1 minus mu, and I am taking the variate to be t upon root n sigma. So, this raised to n. Now, you expand this, yeah, remember this is when you are writing this. So, I am just expanding my T x, and this will be expectation of 1 plus T x plus T x whole square by factorial 2 and so on, right, the expansion of e raised to T x. So, that is what I am doing, and then I am taking expectation inside, because yeah, okay. So, now here in the central limit theorem, when I assume that they have finite variance. Yeah. So, another assumption I should have made is that because I am using the MGF way of I am using the moment generating functions to prove the theorem, I should have also said here that MGF x I exist. Okay. And so, obviously, we will be talking about all those t's at which the MGF exists, right, at which the MGF is defined. So, therefore, yeah, I take this expectation, and since the MGF exists, so I can take the expectation inside, because the series is a convergent series, and so I can take the expectation inside. So, this is what you have raised to n, and you see here I am not considering higher powers of t, because see this is square, then it will be t cube, t 4 and so on. So, I am just writing this whole as a higher terms, higher order terms of t, powers of t, right. So, then see expectation of x 1 minus mu is 0, because we have taken assumed that each x I has mean mu. So, this term is 0, and therefore, you will be left with this thing. So, and expectation of x 1 minus mu whole square would be sigma square. So, this is 1 plus sigma square t upon should be t square and sigma square. There should have been a t 2 also, sorry, this will be 2 factorial and so on. So, therefore, there will be a 2 here, right, because t x square upon 2 factorial and so on, right, and then higher terms, higher order terms of t, right, this raised to n. Now, so as n goes to infinity, you see, because n raised to half is in the denominator. So, then when you say take the third power, it will be n raised to 3 by 2 and so on. So, these things will go to 0 as n goes to infinity. So, but here, so I will ignore this, and then you see what happens to this 1 plus sigma square. So, the sigma square cancels out, t square by 2 n. Right. And so, if you write this as t square by 2 into n and then raised to n, So, I hope you know that most of you that this will converge to e raised to t square by 2. Yeah, because n in the denominator and then n power. So, as n goes to infinity, I can safely ignore these terms. So, then this will converge to e raised to t square by 2, because sigma square cancel out, and you are left with t square by 2 into 1 upon n raised to n. So, this converges to t square by 2 as n goes to infinity, right. And you know that this is the MGF of a random variate, which is normal 0 1, right. And so, we have shown that using the lemma, because I have shown that the MGF of this random variable sigma x I minus n mu upon root n sigma, that converges to the MGF of a standard normal variate. Therefore, by the lemma I can assume that this random variable converges to n 0 1 in distribution as n goes to infinity. So, using the MGF, the proof really simplifies, and so in the proof I have used the expression small o of t upon root n sigma. So, the understanding is that this denotes terms of the type t upon root n sigma raised to r greater than or equal to 3. See, in that proof for proving the central limit theorem, I wrote down the terms up to t square, and then I wrote down that the later terms will all be having higher power of t upon root n sigma. So, this is the expression, and see, the understanding is that as n goes to infinity, this is for this expression, that means because r is greater than or equal to 3. So, anyway, this will go to 0. So, that means as n becomes larger and larger, the terms that become very small. So, their contribution is negligible, therefore, we ignore them, right. This is the idea, but now for convenience I have expressed, I have used this term for this notation for also including the term expectation of x I minus mu raised to r. So, that means I am taking that this now denotes for me in that proof this into t upon root n sigma raised to r for r greater than or equal to 3. Okay. But then since we have assumed that the MGF exists for all x i's are all identically distributed. So, the MGFs exist, that means all moments exist. So, all moments are finite, and therefore, these numbers are finite for all r. Hence, the same thing applies, that means if this becomes small, then as n becomes larger and larger, this whole thing also becomes very small and goes to 0, right. So, this is the idea that as n goes to infinity, this will go to 0. So, therefore, we can neglect the term. So, this is, and I have used this expression elsewhere also, and so this the understanding is that when you write small o, then it means that these are higher order terms. Whatever you have written down, beyond that all higher order terms, that means of power higher than 2 here, and for us the way I am using it, are greater than or equal to 3. So, therefore, for large n I can ignore such terms in my sum. This version of CLT as central limit theorem goes under the name of Lindbergh-Levy theorem also. Lindbergh in 1922 and Levy in 1925 independently gave this theorem. They showed they proved this result. So, independent of each other in 3 years gap. So, therefore, this is also sometimes known as the Lindbergh-Levy theorem, but most commonly it is referred to as the central limit theorem. So, the proof is simple, just using the independence, identically distributed random variables and the properties of the MGF. So, through the property of MGF, we could show that this sum of the random variables, which are independent identically distributed random variables, will minus n mu upon root n sigma converges to a standard normal variate. So, now let us look at this interesting example. This is from Dodevich and Mishra, and I will give you the references at the end of the course. So, a casino has a coin and wishes to remember a casino is a people bet, and the game is tossing a coin to show a head. So, a casino has a coin and wishes to estimate p, the probability of a head on any toss, in such a way that they can be 95% confident that the estimate p hat is within 0.02 of p. Okay. So, obviously, they want to have an idea as to how what is the probability that the coin will show a head when it is tossed. It is important to them, because every whenever a head is tossed, then the person who is playing the game wins. So, the casino has to pay. So, therefore, they want to be confident that the whatever their estimate is, that is within 0.02 of p, the actual p, right. And so, weak law of large numbers helps you out here. So, given an epsilon and a delta greater than 0, we know that there exists an n naught, the smallest value of n, such that for all n greater than or equal to n naught, probability of x n bar minus p greater than or equal to delta is less than epsilon, right. So, for all n greater than or equal to n naught, this difference is greater than or equal to delta is less than epsilon, right. And so, the complementary the event would be that probability x n bar minus p in absolute value is less than delta. So, this probability is greater than or equal to 1 minus epsilon. So, the casino for the casino problem, your delta is 0.02. So, that your x n bar is within 0.02 of p, right. So, it can be either a little less than p with that means, it can be p minus 0.02 and p plus 0.02. So, this is what you want. So, your x n bar should be in this interval. So, delta is 0.02 and your 1 minus epsilon is 0.95. So, this probability that your x n bar is in this interval should be the probability should be greater than or equal to 1 minus epsilon. So, that means you will be 95% confident. This is the idea. So, therefore, you just write out this. Okay, this is exactly what yeah. So, once you give the values of delta and epsilon, you get that probability x n naught minus p in absolute value should be less than 0.02. So, this probability should be greater than or equal to 0.95. Okay, this I do not need to write this, because now I am using the value n naught. Okay. And so, when you expand this, x 1 plus x 2 plus x n naught upon n naught minus p. So, this should be less than 0.02 is greater than or equal to 0.95. So, this will so therefore, you can find such an n naught, and therefore, the casino can by tossing the coin that many times, they can find out the the estimate p hat for the probability of p. The same event can be rewritten as okay, this has to be, or it was not really necessary, because since we have said that there is an n naught which will do the job. So, therefore, I could have carried it as n only and then found it out, but anyway. So, therefore, this is everything is n naught here, right. So, now I have this event, and if I divide all the numbers by under root n naught p q, because the variance of each x I is p q, and therefore, variance of x 1 plus x 2 plus x n naught will be n naught p q, and so divide by the standard deviation, and then therefore, this event is the same as this. So, the probabilities are the same, right. 0.02 n naught divided by under root of n naught p q. So, I divide throughout by under root n naught p q to standardize, and therefore, this is my random variate now, which is the standardized variate, and by CLT theorem, this is a standard normal variate approximately, of course, right. Approximately, this is standard normal variate. And so, probability is a function. Now, this probability would come out to be a function of, because your numbers on the two end are the interval in which you are wanting z to be, that probability will depend on p. Now, the thing is that you are see, if I find so here again you have to do n naught n naught. So, the whole idea is that if I put this equal to if I put the maximum value of n naught p q here, then I will get the because it is the denominator, if I put the maximum value, then this will be the smallest. So, if that means this interval will be the smallest for the maximum value of this number, it will be the smallest interval. And so, probability of the smaller interval, if this is greater than 0.95, then for any other p, this probability would be greater than 0.95. That is the idea. So, my event, what I am doing here is, by writing the maximum value for this, this event will be subset of all other events, whatever the value of p, because q is 1 minus p, right. So, therefore, if this probability can be made to be equal to 0.95 or greater than or equal to 0.95, then for all values of p, this will be greater than or equal to 0.95. This is the idea, right. So, therefore, and we know that the maximum n p q is 1 by 4 for all 0 less than p less than 1. We know this. Okay. I am sorry, why am I writing this p q. So, maximum value of p q is 1 by 4, and therefore, the required probability, since by the CLT theorem, this is standard normal. So, this will be okay. Now that we have started doing it, so I will write not everywhere. So, this will be phi of, which is the for the cumulative probability, this is 0.04. So, if I am writing 1 by 4 now, so this will be 1 by 2, and so you take it here, and therefore, the 0.04 and naught minus phi of minus 0.04 and naught, right, from here, right, which by symmetry of the normal standard normal variate, this is 1 minus of this 5.04 under root n naught minus 1 minus this. So, this becomes twice 5.04 root n minus 1, and now we want this to be greater than or equal to 0.95. And so, when I compute the value of n for by putting it equal to 0.95, then again for all values of n greater than or equal to n naught, this inequality will be satisfied, right. Okay. So, the normal tables give me that. So, therefore, this probability becomes 1 plus 0.95 divided by 2. So, now the normal tables tell me that corresponding to this value 0.975, that means the area under the normal curve is 0.975, the corresponding value is equal to 1.96. So, that means 0.04 under root n naught is equal to 1.96. So, from the normal tables corresponding to this probability, I get that this number must correspond to 1.96, and therefore, your root n naught is equal to this, which is 49, and therefore, your n naught greater than or equal to 49 square. So, that means, for that many sample values or that many trials you have. So, this will with this this number n naught, which is greater than or equal to 49 square, your estimate of p, which will be obtained by p hat. So, that means, p hat will be essentially your. So, what we are saying is p hat is summation, or you can say x 49 square bar. So, this estimate of your p will be within 0.02 of your original p with probability 0.95. Okay. So, this is interesting application of your central limit theorem, and because we could reduce the whole thing to computing a standard normal probability, we got the answer here, right. Now, again I will just try to have a variety of examples to show use of the central limit theorem. So, now here another question that is asked is, if suppose you have x 1, x 2, x n, again a sequence of identical independent distributed random variables, and these are Bernoulli random variables, right. Probability x I equal to 1 is p, and probability x I equal to 0 is 1 minus p for all I, and again p is unknown, right. So, you want to estimate this probability, and as I told you that of course, the weak law of large numbers tells you that x n bar will be a good estimate provided n is large enough, right. So, now let us see if you put, so now let us define S n as x 1 plus x 2 plus x n, and let us fix t. So, here in this example I am trying to show you the accuracy of the central limit theorem, and obviously we expect a better answer from the central limit theorem than if I just use the Chebyshev's inequality. So, this is the whole idea by doing wanting to do this exercise. And so, here let us see that so the question is, using Chebyshev's inequality, how large an n will guarantee that this S n which is the sum of these random variables x 1 to x n. So, this divided by n minus p in absolute value is greater than or equal to t is. So, you have fixed the t. So, given a t, then you want this probability to be less than or equal to 0.01, right. And we will now here compare because how large an n. So, Chebyshev's inequality will also give me the answer, give me a value of n, and then central limit theorem will also give me a value of n. So, we will compare the two values, right. So, here expected S n upon n is p, and variance S n upon n is p into 1 minus p by n, right, because they are independent random variables, identical. So, therefore, we will first use the Chebyshev's inequality, and then compute through an estimate of n, and then through the central limit theorem also. Yes. So, applying the Chebyshev's inequality, because expected value of S n upon n is p and variance of S n upon n is p into 1 minus p by n. So, therefore, by the Chebyshev's inequality, probability that S n minus n minus p in absolute value is greater than or equal to t. So, this is less than or equal to expectation of this square divided by t square. In other words, the variance of S n upon n. So, the variance of S n upon n is p into 1 minus p by n. So, therefore, by Chebyshev's inequality we get this estimate, and here again we are applying the same logic. So, I hope that you can easily see that the maximum value, because if you have 0 less than p less than 1, we are in the earlier this thing also I used the fact that max of p 1 minus p is equal to 1 by 4. You can easily check, I mean, okay, let us just spend a minute and try to see. That means, this is a function of p, and I can find out the derivative. So, the derivative would be 1 minus p, 1 minus p by 2, right. And so, this is, I put this equal to 0. So, that gives me p equal to, I am sorry, this is 2 p, because minus p square. So, the derivative is minus 2 p. So, this implies that p is half. Certainly, p cannot be 2, because p is lying between. So, this is a critical value, and to make sure that this gives you the maximum value, the second derivative, that means the second, if I call, if I am saying f p is p into 1 minus p, then f prime p, when you put 0, gives you p equal to half, and f double prime p is equal to minus 2, which is less than 0. So, that means the critical value that we have obtained will be the maximizing value, and so you see p equal to half gives you the maximum of this, and you can also prove this by concavity and so on. Anyway, so therefore, this is less than this, I mean here, and if I am putting the maximum value, then obviously this equality will convert to inequality. This is less than or equal to this. So, 1 by 4 n t square, right, and this should be equal to 0.01. So, we get the estimate for n, maybe I should put this something like this, 1 upon 4. So, your n will be equal to 1 upon 4 t square into 0.01, which is 25 by t square. So, this is your Chebyshev's estimate of this probability, I mean for the value of n, for which this probability would be less than or equal to 0.01. Right. Now, let us try to apply the central limit theorem, and the central limit theorem says that this variate, when you take S n by n minus p divided by the standard deviation, which is p into 1 minus p by n, right. So, you divide by that. So, root n goes upstairs, and this is this is approximately normal, standard normal, right. For large enough n, I can say that this is approximately this. So, now you want to compute this probability greater than or equal to t, and here again I will write this as, so I am standardizing it, and therefore, dividing the whole thing by the standard deviation. So, that gives me the right hand side as root n t upon under root p 1 minus p. Okay. So, here again, because this is greater, remember. So, then if I put the maximum value, as again I had argued earlier, this becomes a smaller interval, and therefore, oh, I should have said, I think we have missed out on the this thing, sorry, the absolute value, right, and here also it should be the absolute value. Fine. So, the standard, so the interval, as I said, if you put the maximum value here, then this becomes smallest, and so the interval is smallest. So, if the probability is and then we are wanting the, so for larger interval, the probability would be higher. So, therefore, if I am taking the smaller interval, the probability I am wanting to be, what was our this thing, the problem that the problem stated was that this should be less than or equal to 0.01. Okay. So, if I am saying that this should be greater, and so here if I am writing the maximum value. So, what will it be? That means, I am wanting the mod z to be greater than or equal to z naught, and if I am taking the smallest value here. So, that means, if this is your 0, then you are asking for yes. So, you are asking for this probability and this probability to be less than or equal to this. Now, if I am taking the minimum value here, that means, I am putting the maximum value here, then obviously, you will be taking larger area. So, therefore, the value of n, which satisfies for maximum value here, will satisfy for all values of p, right. Okay. So, this is the idea. Now, let us see. So, this greater than or equal to, so therefore, I am substituting 1 by 4 for p into 1 minus p, which gives me half, and so that makes it 2 root n t, right. So, it is just the same argument, you draw the figure and you can verify for yourself. So, now, you see this is greater than or equal to 2 root n t. So, let me just show you the details here. That means, we are asking for probability z greater than or equal to z naught, right, which is the same as probability z greater than z naught union probability z less than minus z naught, right. This is the absolute value. As I said, z greater than z naught and z less than minus z naught, right. Now, these are disjoint events. So, therefore, I can write the probability of the union as the sum of the probabilities. So, this will be probability z greater than z naught plus probability z less than minus z naught. Okay. And so, this becomes 1 minus probability z less than or equal to z naught, and probability z less than minus z naught. See, here again I can just show you the. So, that means, if you have your, so if you are wanting z less than, this is minus z naught, you are wanting this probability, but that is the same if you write z naught here, this is the same as this probability, right. So, therefore, probability z less than minus z naught is 1 minus of probability z less than z naught. So, z less than z naught is this whole probability. So, from 1 minus I will get this, which is equal to probability z less than minus z naught, and therefore, I get this. So, this is 2 minus twice probability z less than or equal to z naught, where z is your standard normal variant. Okay. And so, so the same thing I have used here, right. Okay. This is your z naught. So, this whole probability is 2 minus twice phi 2 under root n t, which should be equal to 0.01. So, like we are finding the value of n for which this will be equal, and then higher values of n, this will always be less than 0.01. Okay. And so, this is 0.01. Therefore, this tells me that phi 2 root n t, right, if you bring this to this side and this here, is something wrong? Okay. So, you bring this to this side and take this to this side. So, it will be 1.99 divided by 2, which is 0.995, and so you look up the standard normal tables, and corresponding to this probability, the corresponding value of the variate is 2.57. So, from the normal tables I get that when this number is 2.57, the corresponding normal probability from minus infinity to 2.57 is 0.995. Okay. So, therefore, this gives me root n as 2.57 upon 2 t. So, the number by the central limit theorem, the estimate, and therefore, this implies that your n is 2.57 upon 2 t whole square, right. So, this is our central limit estimate, and that is our Chebyshev's inequality estimate. Now, if you want the third part of the question is compare the results for t equal to 0.01. So, for t equal to 0.01, the Chebyshev's inequality gives you a number, a value of n, which is 2500,000. That means 250,000. 250,000, whereas the central limit theorem will only ask for this many sample values. So, if you want to estimate the get the sample size such that S n upon n differs from p in absolute value by this difference. So, that means the probability that this is greater than or equal to t is less than 0.01. So, that number for central limit theorem is much smaller compared to the Chebyshev's inequality. So, this was another aspect of central limit theorem, which I thought you should have a look at. Okay. Then another usage of central limit theorem is to how we approximate the chi-square distribution for large values of n. Because you see somebody has already done the calculations for the central limit theorem for the normal variate, standard normal variate. So, we can make use of those tables to compute chi-square distribution large values, for when the n is large. So, the idea here is that if you take x 1, x 2, x n are again identically independently distributed random variables, each is chi-square 1. So, this implies that expectation of x I is 1 and variance of x I is 2, right. And then also we know from the reproductive property of chi-square, in fact, through the joint MGF also we can show, and even otherwise we have seen that because each of them is independent identically distributed chi-square. So, x 1 plus x 2 plus x n will be chi-square n, right. Through this is we have already seen it in one way that this when you sum up these independent identically distributed random variable. So, chi-square has the reproductive property. So, this sum S n is chi-square n, and later on we will also show through use of MGF how quickly you can say that this sum will be chi-square n if each is chi-square 1, right. So, anyway, now, so by CLT theorem S n minus n upon root 2 n in distribution, because we have standardized it, right, subtracting the mean of S n. So, S n will be the mean of S n will be n, because each is chi-square 1. So, therefore, this is minus n upon root 2 n, that will go in distribution to 0 normal 0 1, right, as n goes to infinity. So, or in other words, chi-square is the mean n, normal approximately you can say mean n and with mean n and variance 2 n. So, this is a normal, whichever way you want to put it. So, therefore, you want to compute this probability. Remember, for large n you want to be able to compute these probabilities using the normal tables. So, therefore, when I standardize, this will be S n minus n under root 2 n. So, this will become a minus n upon under root 2 n, right, which is the value phi of a minus n upon root 2 n. So, therefore, when n is large, the central limit theorem will give me a good approximation, and so for large n this will be a standard normal close to a standard normal variate, and therefore, I can compute this probability for large chi-square n by the normal standard normal table. So, now I said I will show you how we can approximate the chi-square probabilities using central limit theorem. So, let n be 100 and we wish to. So, I had shown you that the formula, I gave you the formula, that means you can standardize the chi-square random variable, and by using the central limit theorem you can get the probability. So, let us compare the values for n equal to 100, right, and we want to approximate A. So, that chi-square 100 less than or equal to A, the probability that chi-square 100 is less than or equal to A is equal to 0.95, right. So, by using the central limit theorem, right. And so, central limit theorem said that this can be converted to, see, right, 5 chi-square 100 minus the mean is 100 divided by variance is 200. So, under root 200. So, that becomes phi of A minus 100 upon under root 200. So, this will be approximately because we are saying and let us see how if n equal to 100, how good, I mean, is it large enough for a good approximation. So, if you put this equal to 0.95, then by the standard normal tables, the 0.95 probability corresponds to this value being equal to 1.645. Okay. So, therefore, you equate these two numbers, and that gives you A equal to 100 plus under root 200 into 1.645, and that comes out to be 123.2638. Okay. So, using the central limit theorem, and then we just standardize this variate, right, and then we said that if n is large enough, this must be approximately normal 0 1, and so from there I get this probability. Now, from the tables for chi-square 100, if you compute the exact value, then exact value of A, that comes out to be 124.342. So, you can see that the approximation is really very, very good, and this is for n equal to 100. So, the point we are making is that if your n is larger, you will get a better approximation, better than this, even the difference will be only at the decimal places, and so you can use your standard normal tables for computing these probabilities. So, this was another point that I wanted to make about using central limit theorem results. So, now another application of central limit theorem. The question is, if x 1, x 2, x n again are identically independently distributed random variables, and you are given that expectation of each variable is mu, and the variance is sigma square, and also that the expectation of x I minus mu raised to power 4 is sigma square plus 1, which is less than infinity, right, because sigma you are taking to be a finite number. So, the first question is, does the weak law of large numbers hold for x 1 square, x 2 square, x n, I mean the sequence of square of the random variables. And the second question is to find limit of this probability, okay, where x 1 minus mu whole square plus x n minus mu whole square divided by n. So, we are talking in terms of the squared random variables. So, because the central limit, the weak law of large numbers holds for x 1, x 2, x n, because your variance and mean are finite. So, now the question is that does the weak law of large numbers hold for x 1 square, x 2 square, and so on, the sequence of squared random variables. So, therefore, we need to for answering part A, I need to say that the variance of each x I squares is finite, right. And for this, I have just made this calculation that if you open up this expectation of x I minus mu raised to 4, because that is what you are given as sigma 4 plus 1. So, yes, and we missed this point, that for the weak law of large numbers, I need to say that these xi squares are identically independently distributed and they have finite variance. So, now we have done enough of this thing to say that if x 1, x 2, x n are identically distributed, then obviously xi squares are also identically distributed, right. This much of probability theory we have done so far, and then that they would be independent will also follow, right, because if x 1, x 2, x n are independent, then these will also be independent. So, I am sure you can work it out by all that we have done in the course by now. Okay. And now, to show that the variances of these xi squares are finite, which will be the same. So, I have just done this exercise, and surely there may be other ways of doing it also, showing that the variance is finite. So, anyway, I just opened up this expression, then I took expectation inside, and you can see that here for example, expectation x I cube, then into mu, and then when you get 6 x I square. Now, expectation of x I square I know, which is sigma square plus mu square, right, because that is already given to me, and then there is expectation x I is mu. So, therefore, this is what you get, mu 4 minus 4 mu 4 plus mu 4, and here it is 6 times sigma square plus mu square into mu square, right. And then you can write down this thing here, and this then tells me, see for example, here this is 3 mu 4, because this is 6 mu 4 minus 4 mu 4 plus mu raised to 4. So, that is 3 mu 4, and this is c sigma square mu square. So, yeah, you get something like these two expectation of x I raised to 4 minus 4 times mu x I cube, this is equal to a finite number, and therefore, we can conclude that both are finite, right. And so, weak law of large numbers can be applied. So, therefore, I needed this condition, if the xi's are identically independently distributed, and if the fourth power expectation about the mean is finite, then the weak law of large numbers can be applied. Okay. And now, this probability, we just need to again standardize our this thing. So, summation I varying from 1 to n, summation I varying from 1 to n sigma x I square whole square. Now, variance of x I minus mu whole square, summation variance of each x I mean when you want to compute the variance of x I minus mu whole square, then you are looking for yeah, I should have said this is variance of x I minus, that is okay, variance of x I minus mu whole square, then expectation of x I minus mu raised to 4 minus expectation of x I minus mu whole square, right, this expectation squared, right. So, which now since we are given this number, which is sigma 4 plus 1, and this is expectation x I minus mu whole square is variance of x I, which is sigma square. So, raised to 2 will be minus sigma 4. So, the variance of each of this x I minus mu whole square is 1, right, and therefore, variance of summation I varying from 1 to n x I minus mu, maybe I can rewrite this nicely, so that it is readable. So, then what we are saying is that variance summation x I minus mu whole square I varying from 1 to n, this is equal to n, because each of them has variance 1. So, by central limit theorem, this summation I varying from 1 to n minus sigma square divided by root n, right, because each had variance sigma square, mean of x I minus mu whole square is sigma square. So, then n sigma square divided by n, so mean is sigma square divided by root n, right. So, this goes to n 0 1 in distribution as n goes to infinity, and therefore, the required probability, yeah. So, therefore, I have divided by this thing here we are doing this, and yes, root n. If you want to write this as I can just multiply by root n throughout, something is you are wanting this to be less than or equal to 1. I am making it x I minus mu whole square n minus sigma square, and then you are dividing by n, by root n. The required this thing, we are looking for 1 by root n. So, a variance x I minus again this is summation, variance summation x I minus mu whole square divided by n will be n upon n square, which is 1 by n. So, therefore, you will divide by 1 by root n. 1 by root n, and so that if I bring 1 by root n here in the denominator, then this becomes 1. So, therefore, because this goes to standard normal, this whole thing as n goes to infinity. So, this required probability, see absolute this less than or equal to, I have divided by 1 by root n. So, this becomes less than or equal to 1. So, this is twice phi 1 minus 1. We have already done this so many times in the absolute values. So, this is 2 phi of 1 minus 1, and again from the standard normal tables, this is 0.8413. So, this number. So, therefore, 2 into 0.8413 minus 1, and that comes out to be this. So, integrate probabilities and so on. The results, there is no end to the results, and I will try to I think I will continue with the discussion on the central limit theorem in the next lecture also.